Hello everyone, this is Brock Skaggs, and I'm going to make a couple of videos here dealing with torsional loading of shafts. And so the item that comes to mind is a typical drive shaft in your vehicle there that's basically under this twisting load. And so our simplified drawing is this shaft. It's got two different sizes as far as cross-section wise. Also the cross-sections are different. One's solid and circular in section AB here, and then the other one's more tubular in shape with a outer diameter and inner diameter in BC. We've got a couple, think of these as V-belt pulleys, sprockets, sheaves, gears, whatever they may be here. A couple items that are causing concentrated torques to be applied at points A and B here. And the only thing we need to know is at point A, there's a torque going in the counterclockwise direction with a magnitude of 20 foot-pounds. At B, another torque about the axis of the shaft causing a magnitude of 50 foot-pounds of torque in the clockwise direction. As far as lengths, you can see AB is 2 feet, BC is 3 feet there. Assuming the same material all the way throughout, aluminum, 661 if you will. So a shear modulus there of 3.75 times 10 to the 6 psi. And so for this video, we'll just look at task number 1, and then I'll start another video where we look at task 2 there. And so task 1 is going to be determining the maximum torsional shear stress experienced by each section of the shaft. And so each of these sections of the shaft, and that being A, B, and BC, they have different cross sections. So that's going to be a contributor to them having different shear stresses, as well as they are going to be carrying different magnitudes of the torques that they feel there, just because of the way we have these concentrated torques being at different points along the length of our overall shaft there. And so that'll be where we're looking in this video. As far as talking about the next video, we'll talk about the actual deformations of the shaft. If I'm on A and I'm looking back to C, I'm rotating. Am I rotating clockwise, counterclockwise, and how much there? And so with that being said, let's go ahead and hop right in to our discussion. And so for the first part, determine the maximum torsional shear stress. There's one formula that's coming to mind immediately for me, and it is tau max is equal to TC all over J. And this is for the maximum torsional shear stress experienced by a nice circular cross section. We're assuming we don't have plastic deformation here, so that's one thing. If we were doing our due diligence, we could calculate this tau max value and check it against the yield strength and shear of the material, just to confirm. And then what do we have as far as variables? We've got the torque. The C value is essentially that outer radius value associated with a circular cross-section, and J is a cross-section property called the polar moment of inertia there. And so for a solid circular cross-section, it's pi over 32d to the fourth. And so with that, that's kind of the little bit of background and theory as far as the fundamental equation we'll be using. One of the problems, though, is I need to find the torque in each section, the torque in section AB and the torque in section BC. And so that'll be our first task, really, is to determine those values. And just like a lot of the mechanics problems we've been looking at, we're going to use a little bit of statics in order to help us out here. And so what I'm going to do is draw a free body diagram where I cut the shaft right about the middle of section AB and also right about the middle of section BC. Those are two separate free body diagrams. Each time I'm going to take the very far left extreme end. That way I don't have to figure out this reaction torque happening back at C. And so I'll jump right into that, draw a free body diagram of AB first to get our wheels turning here. And so here, got a free body diagram going. It's of section AB. And if I draw that free body diagram, I'm going to include this first pulley here. It's got a little depth to it here, and then I've got a shaft coming off here, and this is where I'm cutting through the material of the shaft, let's say right there. As far as externally applied loads, we've got the T sub A going in the what I'll call counterclockwise direction. And then I'm going to draw TAB, this internal torque, going in the opposite direction here. And all the time I'm thinking my perspective is always going to be right here, where I'm down and to the left looking back up and to the right at this system. That way when I write my equilibrium equations, I have a constant frame of reference there, and I don't accidentally switch my frame of reference halfway through writing my equilibrium equation. As far as I'm going to say, I'm going to sum the torques here for it to be in static equilibrium, and when I say that, I'm basically summing the torques about this axis here that's running right along the axis of the shaft. And so we're assuming this thing's in static equilibrium. That is a complete free body diagram, and now we're ready to write our equilibrium equation. And so we'll say the sum of the torques, or twisting moments, positive being counterclockwise from the perspective of my little eyeball down here, is equal to what? I'd have positive T sub A, that looks like it's going in the counterclockwise direction, and then minus TAB, it's directed in the clockwise direction. We set that equal to 0, and we solve for our internal torque TAB, which here very simply is just equal to TA, and that is 20 foot-pounds. One thing I'm going to go ahead and do is also convert 20 foot-pounds. I want to get that to inch-pounds eventually. So I'm just going to make my quick little conversion step right here and say, hey, that's equivalent to, it looks like 240 inch-pounds. All right, and so now what I have is the amount of torque carried by section AB of this shaft. And so now we just need to repeat the process and find out the amount of torque carried by section BC. And I'll just do that right over here to the right. And so let's get a little line here to divide us out. And here is going to be the free body diagram. Now I'm going to make the cut in section BC. And so if I look back here, here's the diagram. I'm going to make this free body diagram cut right here, right about where it says LBC. And then I'm going to take the left-hand side of that cut, and I'm going to take the entire left-hand portion of the shaft itself here. And so this free body diagram is going to include the torque at A, include the torque at B, and then we're going to have some unknown value at this point for the torque carried by section BC. And so now we need to, of course, draw our free body diagram. So I'll get my pen going again. Here's the smaller of those two pulleys at A. Come back here, we've got the bigger pulley at B. And then back behind it, we've got some material, and then we made a cut here. As far as the externally applied torques, that would be the T sub A and T sub B that we have above. And so T sub A, just to remind us, is going in the counterclockwise direction, and T sub B is going clockwise. And so I'll come down here. Here is T sub A, and there's T sub B. And here I don't really know which direction this is going. I'm going to say in this direction here, just for a guess, and we'll call it TBC. Again, I always draw my little eyeball here to keep a reference so that when I write my equilibrium equations, I'm always keeping the same reference and not having to flip back and forth, which will mess up my signs. And so just taking a quick moment, looking back at the diagram, looking at our free body diagram, it appears that I do have all of the necessary loads on the free body diagram. And now I can write my equilibrium equation. So we're really doing the same thing here, just a little bit more complicated because we've got another term in there. And so we'll say, well, the sum of the torques, counterclockwise being positive, again taking the axis we're summing the torques about being that longitudinal axis of the shaft. And if I just work from the bottom left up, I've got positive T sub A minus TB. It's going in the clockwise direction. And then I'd have plus as well on the TBC. And so we're setting that equal to 0. And now we're solving for TBC. So TBC here is equal to TB minus TA. Which is our 50 foot-pounds minus the 20 foot-pounds. So here I'm going to have 50 foot-pounds minus the 20 foot-pounds, which gets me a value of 30 foot-pounds. And so now I know the internal torque carried by section BC of the shaft has a magnitude of 30 foot-pounds. Also, the number is positive, so that means my direction here, as far as TBC being oriented in the counterclockwise direction, is correct. Very similarly, on AB, I got a positive number from my equilibrium equation, so TAB, the direction I assumed on the free body diagram, is correct as well, and it's actually going in the clockwise direction. So we've actually got these internal torques oriented in the opposite directions from each other. And so first thing, I'm going to go ahead and convert this over again. 30 foot-pounds, 12 inches per foot, gets us to 360 inch-pounds. All right. And so now that I've got the torques carried by each of the shafts, I'm very close here. Now I just need to work through some cross-section properties. So I'm actually going to extend this line down a little bit farther, and we should be able to calculate the tau max value for AB and for BC. And so here I'll first do it for AB. And so this is for AB. And we'll say, well, tau max is TC over J is our starting equation. Well, the T we know, that's the torque in AB. The C is just the radius. This is a solid circular cross-section, so I'm just going to write diameter over 2. And then the J is pi over 32 d to the fourth, that moment of inertia for a solid circular cross-section. Working around the algebra here, I believe we're going to end up seeing 16t all over pi d cubed here when it's all said and done. And so then it's just a matter of plugging and chugging, right? 16, our torque for AB was 240 inch-pounds. Got pi and the diameter cubed in the denominator. My diameter for section AB was the 1 inch. We ensure to grab the right properties associated with each section of the shaft. And then I'll compute the value here. So 16 times 240 divided by pi is approximately 1,222.3 psi. And so we would say that's the maximum torsional shear stress experienced in section AB of the shaft. And so now we'll just repeat the process for BC here. And so got section BC over here. Again, same base formula that we'll be working out of. Tau max is TC over J. Here we've got to be a little bit careful. The torque is still just the torque carried by BC. We said that was 360 inch-pounds before. Now it's a hollow cross-section, right? BC basically has an inner diameter and an outer diameter there. And so here we need to make sure the C value is the outer diameter over 2. And our polar moment of inertia also changed a little bit because it's going to be pi over 32 d outer to the fourth minus d inner to the fourth there. So basically you can think of it as calculating the polar moment of inertia associated with the circle on the outside, and then we're subtracting the polar moment of inertia associated with the circle on the inside there. And so after we realize that, it's just again plugging and chugging at this point. We've got the torque at 360 inch-pounds. The diameter for the outer, I believe, is 1.25 inches. The inner is just 1. So this is 1.25 inches over 2. We'll zoom in just a touch here. And then for the denominator, we've got pi over 32, 1.25 inches to the fourth minus the 1 inch to the fourth for the inner diameter. And that expression should yield us the maximum torsional shear stress experienced by member BC here. So just give me 1 second to run this through the calculator. And I'm getting right about 1,590 psi. There we go. And so it's about 15 minutes, so we'll stop here. As far as the takeaways, very last lines here. we were after determining the maximum torsional shear stress experienced by each section of the shaft, and that's what we've done. AB here, we worked through our free body diagram to figure out the internal torque, used our tau max as TC over J expression or equation to compute the maximum torsional shear stress, came to a value of 1,222.3 psi, and then for the second half of the shaft, BC here, same idea, used a free body diagram and our equilibrium equation to get the internal torque. Then the base formula we were working out of was tau max was TC over J. Here it's a hollow cross section, so we've got an outer diameter and inner diameter to work through. And so I had to make that adjustment here. And then after recognizing that, it was just plugging and chugging with the known values to get to 1,590 psi. And so I'll stop this video at this point, and we've completed task 1, and then I'll pick up in a second video for task 2, where we investigate the angle of twist associated with this torsional loading. As always, thank you for watching the video, and hopefully it helps you with your mechanics and materials.